Hi, I'm Matt Mellis. I'm an aerospace engineer for NASA, and I worked on the shuttle program for a good number of years. And I'm here with my colleague today, Kevin Burke, who participated in the acquisition and deployment of the 30 or so clips that you're going to see in just a few minutes. Now, and Kevin, thanks for being here today.
Glad to be here, Matt.
What you're going to see is what I consider to be the best of the best, state-of-the-art imagery on both film and high-definition video that the Space Shuttle program is capable of producing today. And not only does it serve a technical purpose, and we'll get into a lot of that detail as we get into the movies here, but it also serves as an enormous inspirational and educational aspect for all of NASA's stakeholders. There's a number of intents that we have for this production, and one of them is to pay tribute and commemorate the shuttle program, which has essentially been a 30-year program, and it's nearing completion as we go to final print with this production. We also want to pay tribute to the men and women that made all of this imagery possible over the years of different missions and launches that we've had. And also to give a view that not very many people see outside the NASA family of these fantastic pictures that are used largely for engineering purposes, and to let everyone on the outside of the NASA family have insight as to what goes on with the shuttle when it launches. I think this is a very moving set of clips that you're about to see. We're opening here with this somewhat stylized view of one of the launch sequences that actually is going to play out in the upcoming clips. And I've got a little soft focus on it, and thought we would open it up with a couple of fun facts about the shuttle. It really is an amazing piece of equipment. It has phenomenal amount of fuel that it burns over the 8 minutes during its trip to orbit. And when they get up there, in that short 8 minutes, they're going about 5 miles a second, which is a pretty spectacular achievement for a piece of machinery. So this is how it all happens. This is how the machine does its job, and the film speaks volumes.
This is camera view E19. We commonly refer to this as Echo 19. And it's a 16 millimeter camera with a 10 millimeter field of view for the lens, the focal length of the lens. And it's running at 400 frames a second. So the effective shutter speed is really 1/1200th of a second.
Yeah, it's pretty amazing. I mean, this is all a slow motion event. And basically you're going to see the 6 seconds prior to launch of the vehicle as the Space Shuttle main engines turn on. Now, the purpose of this camera, they all have different purposes. Most of these, if not all of these cameras that you're going to see in this production, are engineering cameras to look for different engineering aspects of the launch process. And so the purpose of this one is to check to make sure ignition is going off okay, which is what you're seeing here. Main engine start is just happening, and you can see the engines are starting one at a time. This particular camera looks at engines number 1 and 3, right? Is that what this is?
Yep.
And so you can see them, they're starting to fire up. Those sparkers that you see are there to make sure that any unburned hydrogen gets ignited before it floats around and collects in some place where it can ignite later and cause problems. Again, you're seeing the engines sort of turn on here. And so we're roughly coming into about 5 seconds before liftoff. The computers are checking and validating that everything's A-OK. And there's a little bit of a pitch over that the whole vehicle does as a consequence of these engines thrusting off the center of gravity. And when the whole vehicle snaps back and is straight up in the air, the engines or the boosters ignite and the whole thing takes off. Great photography here. I mean, you can see all this flow phenomenon going on inside the engines. Now, the Space Shuttle main engines are burning hydrogen and oxygen, and I'll talk about some of the fun facts about that later on in some of the other clips that you're going to see. But here you can see the engines have stabilized, and everything is A-OK. And in just a few moments, you'll see the boosters fire off. Did we talk about the time code? I can't remember. So
No, we haven't talked about the time code. The time code that you'll see, the LED display on the right-hand side, is actually positioned between the two sprockets on the 16 millimeter frame. And the time code is UTC time code. It's an IRB format. And you'll see that it's 21 hours, being UTC at 5:02 p.m. local time, 2 minutes, 11 seconds, and the three digits that are moving in the upper right-hand corner would be representing 1,000th of a second. The solid number 1, the second digit from the top, is indicating the synchronization of the camera as more of a technical parameter. And that is on every camera to synchronize the field of view, to synchronize the time.
This is pretty cool. You can see some of the oxygen, that cloud of vapor there was from the oxygen fuel umbilical. Of course, the solid rocket boosters have now ignited, and the whole vehicle is lifting off the pad. And you can see sort of the glory of this moment. I mean, there's an enormous amount of fuel being burned. One little thing that I love is if you look at the sky in the background, and this was a very clear day. These pictures were selected, or these movies were selected because of the wonderful photography that we got on this day. And you can see the sky deep into this dark blue, and that's because, as Kevin will talk later on, that we got into color correction that we do post launch to make sure that we're capturing all of these the events that are going on, all of the flow events. So here the vehicle is clearing the pad, and we're on our way.
This view that you're seeing here is camera E8 or Echo 8, and it's a 16 millimeter camera with a 10 millimeter lens.
Yeah, you can see the boosters now coming off the pad, and one of the amazing things that a lot of folks don't know about the shuttle is bolted to the mobile launch platform is it's basically through 4 bolts on each solid rocket booster. And the intent of these cameras is to watch that bolt, which is an explosive nut bolt arrangement, and the bolt weighs about 100 pounds, I should say. And these nuts fracture, and the bolts slap down into a holder that you're actually sort of seeing in the foreground here. And they literally release the vehicle from the pad and allow it to take off. So, for obvious reasons, we have a camera on each one of these explosive hold-down posts, and to make sure that they're operating. They're a critical aspect to the launch process. We want to make sure that they're operating good. So you can see that puff of smoke coming out. And actually, if you want to put the remote on a frame-by-frame stop action, you can actually see the flash as it explodes. Now, Kevin, here's where you guys really did a fantastic job of capturing the detail in the plume through this automatic aperture on the cameras. You want to talk about that a bit?
Sure. Many of the 16 millimeter cameras that are on the MLP and pad structure have an automatic exposure control. It's the only real way to keep the exposure, the high dynamic range exposure, from pre-ignition of the SRBs through the liftoff out of the frame of view. So the camera has basically an automatic exposure.
Right. Now look at the sky on the left thing, and see how it gets dark actually on both sides. You can see how it turns that deep blue. That's the automatic aperture in action right there, right?
Allowing it to see the detail in the pad structure and also in the flame.
Yeah. I mean, when you see a launch in real life, you can't see any detail with the naked eye in the plume. It's just like looking into the sun almost. It's so bright. We can see some of the water from the launch pad. There's a cooling water that comes out. We'll talk about that later. That's splashing onto this quartz protective glass that the camera's behind. Of course, they're in these explosion-proof containers, right, to keep the cameras safe and sound. No cameras were harmed in the making of this movie.
That's right. The cameras are in an explosion-proof box, which is nitrogen purged, and the quartz glass on the front protects the lens. In most cases, there are some cases where there's damage, and if that's the case, the lenses will be repolished, reground, or whatever's necessary to bring them back into optimal condition. Well, at this next view coming up is Echo 18 or Camera 18, and it's a 10 millimeter lens, and looking at the TSM or the tail service mast carrier disconnect.
Yeah, the umbilicals, there's one on each side of the orbiter, one for the liquid oxygen fueling and one for the liquid hydrogen fueling. Those are primary purposes. You can see there's a lot of other instrumentation on these things in feed lines. But these cameras, their intention is to make sure we get good retraction of this, and there's actually a huge 20,000-pound mast that pulls these things inside the tail service mast for the door to slam shut and protect them from the the hostile environment on the outside. Now these umbilicals are about 4 feet wide by 6 foot tall, so you don't really get a sense of scale when you're looking at these in these movies. But they're as big as an average-sized human being, so they're quite large.
One of the interesting photographic challenges that we run into in photographing the TSM carrier disconnect from the inside of the tail service mast is once that door closes, it's pitch black in there. So there's a set of series of tungsten lamps that provide illumination, and the vibrations, the tremendous amount of vibrations that are induced during the liftoff, really rattle those lights, and keeping them from having those bulbs break has been quite a challenge. In fact, they are in the process of changing those lights over to the new LED arrays that provide more stability and less frequency of having the bulbs go out before the film runs out.
They're a lot more robust to that kind of environment.
Okay, Matt, this is Echo 001, and this is one of the 4 cameras on the edges of the MLP deck. This camera happens to be on the northeast corner of the MLP deck, and it's a 16mm camera, as all the ones on the MLP are, and 10mm focal length. It's a wide-angle view, and the effective shutter speed is about 1/1200th of a second.
For our viewers, you can see that we pulled a little bit away back from the vehicle now. We're taking a little bit of a wider view. There's the SSMEs just firing off there, and you can see the plume in the background growing. In fact, if you look carefully against the plume there, you can see a couple of cameras. Why don't you mention what those are, Kevin?
Those are some OTV cameras, operational television cameras that are used for surveillance of the vehicle. They and are piped back live to the launch control complex. The signals.
So the SSMEs are firing. You can actually see the launch tower on the right-hand side of the screen. And again, they go on for about 6 seconds. Computers are making sure that everything's working. And at T-0, those boosters are going to fire, and you'll see a big puff of smoke come out of the flame trench there, and it'll get sucked back down in as the boosters come off the pad. And these two sort of structures, one standing just to the left of the left booster and one standing just to the right of the right booster, are called rainbirds. And there's some piping sort of flat against the launch pad as well that sort of connect all these things together. There go the boosters firing. And all of this fresh water, 300,000 gallons to be exact, comes pouring out of those rainbirds and onto the launch pad to deaden the acoustic noise and cool the pad down. So that's where the water comes from in some of these camera shots.
And here you can see the AEC, the automatic exposure control on the cameras, taking over as the booster plume comes into view, and allows to see the AEC allows you to see the detail both in the plume as well as in the vehicle and the structure itself. And you can also see very good detail on the deck of the MLP.
Now, we talk a little bit about the purpose of each one of these cameras, and this one is to look for some structural anomalies on the vehicle, some thermal insulation failures we might have on the tiles or the blankets, etc., and how the water is getting dispersed on the pad. And also we're looking at debris, and actually you can see here that we've got quite a bit of debris in the field, and debris is a big concern. And also to give a view that not very many people see outside the NASA family of these fantastic pictures that are used largely for engineering purposes, and to let everyone on the outside of the NASA family have insight as to what goes on with the shuttle when it launches. I think this is a very moving set of clips that you're about to see. I consider to be the best of the best state-of-the-art imagery on both film and high-definition video that the Space Shuttle program is capable of producing today. And not only does it serve a technical purpose, and we'll get into a lot of that detail as we get into the movies here, but it also serves as an enormous inspirational and educational aspect for all of NASA's stakeholders. There's a number of intents that we have for this production, and one of them is to pay tribute and commemorate the shuttle program, which has essentially been a 30-year program, and it's nearing completion as we go to final print with this production. We also want to pay tribute to the men and women that made all of this imagery possible over the years of different missions and launches that we've had. We're opening here with this somewhat stylized view of one of the launch sequences that actually is going to play out in the upcoming clips. And I've got a little soft focus on it, and thought we would open it up with a couple of fun facts about the shuttle. It really is an amazing piece of equipment. It has phenomenal amount of fuel that it burns over the 8 minutes during its trip to orbit. And hi, I'm Matt Mellis. I'm an aerospace engineer for NASA, and I worked on the shuttle program for a good number of years. And I'm here with my colleague today, Kevin Burke, who participated in the acquisition and deployment of the 30 or so clips that you're going to see in just a few minutes. Now, and Kevin, thanks for being here today.
Glad to be here, Matt.
What you're going to see is what